Okay, so let's start our class. So today we start from the nature of plasma, the first chapter. The nature of plasma, and we can begin with the molecular model. From the molecular model and the atomic model, and then we can see what's the difference of plasma state, plasma state, compared with other state of matters. Okay, so from the simplified figure, here is a hydrogen molecule. Hydrogen molecule. Okay, so a hydrogen molecule is made of two hydrogen atoms, made of two hydrogen atoms. So we can use a simplified model to draw a hydrogen molecule. So for each hydrogen atom, it is composed of a proton with one positive charge and an electron with one negative charge. So the negative charge and positive charges are balanced. So it behaves like a neutral atom. So this is the model of hydrogen atom. And if you bring two hydrogen atoms close together, they will form a hydrogen molecule. So in hydrogen molecule, there are two protons and two electrons. So this is the basic of simplified model of atomic structure and molecular structure. Okay. So in the hydrogen atom, the charge are balanced, and the electrons cannot move far away from proton. Cannot move very far away because there are forces, including electrostatic force, to bring negative charge and positive charge together. So you cannot separate the electron from the proton in a hydrogen atom. Okay. But if you apply enough energy, it is possible to pull out the electron from the the hydrogen atom, so that the proton and electron are separated to a distance. The distance scale is much larger than the diameter of hydrogen atom. So in this circumstance, the electrostatic force between this electron and the proton become very small. So that in a space, if there is only start with one hydrogen atom, and then you separate electron from the proton, right? Hydrogen atom is made of one proton and one electron. If you separate them so that there is no strong interaction force between this electron and this ion, and we can call this state as an ionization state. Okay, or this process as the ionization process. Okay. So if in a space there are many hydrogen atoms, and most of the atom, or a large ratio of the hydrogen atoms get ionized, and then there will be many protons and many electrons. So these electrons will not attracted by individual protons. So in other words, the electron can travel or move freely. So this electron looks like a free electron. Okay. And in this picture, we can see there are many protons and many electrons. They can distribute it in a space, or in a system we considered. And number of electrons and number of the protons are equal. So in this space, the charge, the negative charge and positive charge are balanced. So there is no net electrical charge. So the state is still neutral, just like the hydrogen atom, the model here. This is one hydrogen atom, right? The electron is bounded, right, and surrounded on the surface of the proton. And the charge are balanced, so the negative charge and positive charge are balanced. So the hydrogen atom is neutral. It's neutral state, right, in a neutral state. And the plasma is also in a neutral state. Sometimes we call this as quasi-neutral or quasi-neutrality. Okay. Because when you set up or when you build up a system and generate plasma, and because of the different behaviors of electrons and ions, so some electron will lost, okay, to the boundary or to a chamber wall. So in reality, in a plasma volume, positive charge is a little bit higher than negative charge. So it is not really neutral, but close to neutral. So the plasma is a little bit higher, it's a little bit higher positive charge. And then later on, when we learn the ways to generate plasma, there are different ways. And one way is to use electrical force or electrical energy to generate plasma. So in that case, we have to know the potential distribution in a plasma system. So when we consider the potential of the plasma compared to the ground or to a chamber wall, we can find out the potential of plasma usually is higher than ground potential. So the plasma is little bit positively biased. It's little bit positive potential. Okay, so this is the basic phenomena of plasma. And since in this figure we can see, compared to the hydrogen atom and the ionized state, right? The hydrogen atom, right, in 1 atmospheric pressure and at standard conditions, the hydrogen is in gas state, right? The hydrogen atom is neutral. But after you ionize the hydrogen atom, electron escape away. So the gas become ionized. So sometimes we also call plasma as ionized gas. Ionized gas, plasma, or discharge, electrical discharge, or gas discharge. So all these terms means the same thing. Okay? Okay, from this figure, we can distinguish the state of matters. So there are 4 states of matter. Before you come to this class, you might know there are 3 states of matter: solid, liquid, and gas. solid, liquid, and gas. Right? And in this figure, the lower axis is temperature, right, in unit of Kelvin. So, at low temperature, there are a lot of metals exist as solid form, right? Like a rock or a piece of metal at a low temperature. They behave like a solid, rigid solid, right? But if you heat up or if you increase the temperature for some materials or some metals, they might convert it to liquid. So for example, if you heat up aluminum metal, right, to a temperature 660 Celsius, 660 degrees C, it is the melting point of aluminum metal. So if the temperature is higher than 660 degrees C, aluminum converted from solid to liquid. So aluminum will become melted. So it will become a liquid state. And if you keep increasing the temperature, and eventually aluminum will form vapor. Aluminum vapor will vaporize. And the industry use the vaporize technique to make aluminum coating. So you can convert liquid aluminum to vapor aluminum. Okay. And if you keep increasing the temperature, right, to here, around 10,000 Kelvin, actually a few thousand Kelvin to higher than 10,000 Kelvin, the vapor phase become ionized and form a plasma state. So in this figure, we can say plasma is the fourth state of matter. Right? The first one is solid, and the second one is liquid. The third one is gas, and the fourth one is plasma. So in physics, sometimes people say the plasma is the fourth state of matter. And in this figure, the lower axis shows the temperature. And the upper axis shows energy in two different units. The upper unit is electron volt, right? And this unit is kilocalorie per mole. So these units can be converted. So if you are interested in chemical reaction, so you would like to know the formation energy. The energy always represented by kilocalorie per mole or kilojoule per mole. So for 1 mole of the reactant, or 1 mole of the reactants, when they undergo the chemical reaction, they need energy, either absorb an energy or release an energy. Right. So this is the reaction heat. You can consider this as reaction heat. Okay. But in physics, people like to use electron volt as the unit of energy. Right. For example, 5 electron volt per particle. 5 electron volt per particle. Okay. And you can convert the electron volt per particle to kilocalorie per mole. For example, like here, 5 electron volt per particle is approximately equals to 100 kilocalories per mole. So you can convert the unit. Okay, so here's the unit, and you can also convert the energy to temperature. So sometimes we use electron volt, or sometimes we use the absolute temperature to show the property of plasma. Okay. So here is the history of the study of plasma. So in 1879, William Crookes demonstrated experiments on passing electricity through gases. So in Crookes' experiment, later on we can see a simple setup. You can make a quartz tube as your reaction chamber. And at two ends of the quartz tube, you can place two electrodes. One electrode is biased positively and the other one is negatively. Or one is negatively or the other one is grounded. So that there will be a potential drop between two electrodes. And if you can control the pressure inside the quartz tube at certain pressure and a certain voltage, certain applied voltage, and then you will see a plasma generated, and the electrical current can pass through the gas. So in 1879, William Crookes showed this kind of experiments. So he can let the electrical current pass through gas, but under certain conditions, certain pressure and certain bias voltage or potential drop between two electrons. Okay. And later on, in 1929, Erwin Langmuir used plasma to describe the step of the matter inside the quartz tube, inside the discharge tube. Discharge tube is electrical discharge, right, between the two electrons in the quartz tube. So Langmuir named this state as plasma. Okay. So later on, people got used to use the plasma to describe this kind of discharge state. And since under these experiments, the plasma are generated from neutral gas. Right? But if you apply bias, very high bias between two electrodes, the electrical field can cause some reactions, and then finally the neutral gas get ionized. Okay. So the plasma is ionized gas, and if you have hydrogen atoms at the beginning, or hydrogen gas at the beginning, after you ionize the gas, each hydrogen atom can release one electron, right? And hydrogen atom become proton, right, with one positive charge. So if we measured, or if we count the number of positive charge and the number of electrons, they should be almost equal. Okay. So this equation shows the positive charge and the negative charge, and most the negative charges are contributed from electron. Okay. So it's difficult to make an ion in gas phase. It's easy to make cation, positive ion in gas phase, but the negative ion is rare. Okay. So here are other sentences to describe the plasma state. So solar plasma is the fourth state of matter. Fourth state of matter. Okay. And there are some definitions. Okay, so usually plasma is coming from the gas discharge. So the plasma state is ionized state. Ionized state. And plasma can conduct electricity. Conduct electricity. So that the current can pass through plasma. Right? The current coming out from anode and then pass plasma and then end up at cathode. At cathode. So plasma can be used as part of the circuit. As part of the circuit. Okay. Once the gas becomes ionized, the plasma becomes a conductor. Before the gas are ionized, the gas is insulated. Gas state is insulated. But after it becomes plasma state, the ionized state can conduct electricity. Conduct electricity. So inside your system, electrons can travel toward one direction, and the cation can travel along another direction. So both cation and the electron can carry current. Can carry current. So the gas, once the gas ionized, they will become a conductor. Conductor. Okay. But the gas still remain as neutral, electrically neutral, because the number of positive charge and the number of negative charge are equal, almost equal. And this kind of behavior is called quasi-neutral. Quasi-neutrality. Okay. So the upper sentence is the classical definition of the plasma. Okay, the behavior of plasma, and there are modern definition. In the modern definition, it's less restrictive. So the ionized gas can be produced by other ways, not just only by the discharge into electrons. Okay. So plasma can be generated by shock wave. Shock wave. And in our class, there's one chapter, microwave discharge. So plasma can also be generated by microwave power. Microwave without electrons. So there are different ways to generate plasma. The upper picture was taken from a system in my lab. So several years ago, we can still run the system. So here is a slit window, and we let the argon gas flow through the chamber and generate plasma by using RF power supply, radio frequency power supply. So once the plasma is generated, you can see the pink light through the window. So here is a quartz window. Okay. So the plasma will emit light. Right. Once you generate plasma, the plasma emits light. Just like the picture you have already seen yesterday. So in this plasma system, we can see the distribution of plasma by looking at the luminous region. Okay. And also in the flashlight lightning, lightning is one type of plasma. It belongs to arc discharge. So in the arc discharge, in this very small region, very small region of the space, the gas become highly ionized. So that the current, right, especially electrons, can flow through this path. And in this lightning, the plasma, the arc plasma, also emit light. And then here is the solar corona plasma. Also emit light. So, and this is a nuclear fusion reactor. Once you start the power and let it operate, there will be a lot of regions full of plasma. And the plasma is also colorful, bright and colorful. And in this slide, we have already known inside plasma there are positive charge particles and negative charge particles. Right? So there are positive charge and negative charge. And most negative charge particles are electrons. So we can say the plasma, inside the plasma, there are electrons and a positive ion. A positive ion is also known as cation. Okay. Okay, so in this picture, this overall shows a volume of plasma. And inside plasma, there are electrons. Right, electrons with negative charge, and there are cation here. Cation, positive charge and negative charge. And if you use hydrogen to generate plasma, hydrogen, at room temperature, hydrogen is diatomic molecule. Right? So most hydrogen remain as the molecule form. So here shows, right, two atoms bound together as a diatomic molecule. So they are diatomic molecules, and they are single atom. But we put a star mark, right, for a single atom. So the star mark means this atom has high energy. And sometimes we call this kind of the high energy atom as metastables or radical. Right? It's neutral and with high energy. Okay. So there are different particles or different species inside the plasma. So actually, plasma is a mixture. So inside the plasma, there are electrons, cations, and neutral atoms, or diatomic molecules. So it's a mixture. And later on we can see the ratio of ionization or degree of ionizations in low temperature plasma is very low. So actually the charged particles inside the plasma is only very small percentage. So most particles in a low temperature plasma or low pressure plasma are neutral. So it's a mix. Most species are neutral. Only small percentage of the particles are charged particles. And the charged particles are mainly electrons and cations. So this is a picture to show the composition of the plasma. And once you generate a plasma, you can see the plasma because the plasma will emit light. So right here, light, for light, we can use H mu to represent photons. Right? So once you generate plasma, the plasma keep emitting photons. And there are reactions which cause photon generation. And later on we can see those reactions in the plasma. Okay, and there are different ways to generate plasma. And the first way is the thermal way. So if we come back to this slide, right? So based on the temperature of your system, the state of matter change. If the temperature is higher than a few thousand Kelvin or higher than 10,000 Kelvin, you can form plasma easily. So based on the energy or based on the temperature. So if you generate plasma by using thermal energy, you generate a thermal plasma. Okay. So this is the first part of plasma generation. Plasma generation by thermal energy. So if you made a system and heat up the gas to higher than 10,000 Kelvin, most gas will become ionized state. So you can generate a thermal plasma. But it is not easy to build a system, right, to heat up the gas to 10,000 Kelvin. Because if you want to build up a system, you need material to make a chamber. So, for example, usually we use stainless steel or quartz to make a vacuum chamber and then generate plasma inside the vacuum chamber. But if you want to use thermal energy to heat up gas to 10,000 Kelvin, right, you will find out even quartz and stainless steel, right, already evaporate, become gas state. So you cannot make a solid system to generate thermal plasma easily unless you have spatial design. Okay, later on we can see the example. Usually it's not easy to generate thermal plasma directly. Okay. In nature, right, the sun is a thermal plasma. So in the universe, there are a lot of the plasma generated by thermal way. Right? But in industry or in labs, if you want to create a plasma, you build out a system. You cannot make thermal plasma. You should use electrical way to make low temperature, non-equilibrium plasma. So the ways to generate thermal plasma and low temperature plasmas are different. Okay. So one requires 4,000 Kelvin to 20,000 Kelvin to generate a thermal plasma. And once the plasma is generated, it is under thermal equilibrium state. And here is the definition of the thermal equilibrium state. So if we come back to this slide, right, we have already known plasma is a mixture. It's a mixture. So there are different particles inside plasma, right? And the energy of the particles can also be represented by the temperature of particles. So for example, there are electrons, there are ions, and there are neutral particles inside plasma. And here, N is the density, right? So N sub E is the density of electron, right? N sub I is density of ion, and here is the density of neutral particles, originally neutral particles. So in a thermal plasma, these three densities are almost equal. And the most important part is here. In the thermal plasma, if there are three kinds of particles, the temperature of these three particles are the same. So the temperature of electron, temperature of ion, and temperature of neutral species are the same. So that the system reach a thermal equilibrium state. So this is a thermal plasma. Thermal plasma, okay. And here's another way to generate plasma. So this is the second way to generate plasma. If we apply electrical field to a system, right? The system is full of gas. The electrical field, if it points from the left to the right along this direction, so this capital E is the direction of electrical field. And inside the plasma system, if there is if there is an electron, and the electron will experience the electrical field, and then accelerate it toward the opposite direction. If you place an electron inside an electrical field, the electron will start moving and get accelerated by the electrical force. Okay. And electrical force, the force equals to the charge of electrons times the electrical field. Right. Small e times the capital E. Okay. This is the force. And based on Newton's theory, F equals to ma. So if what you place an electron here, the m here is the mass of electron. So here, m sub e means the mass of electron. So if you divide it e times e by m, you will get an acceleration. So the electrons will accelerate toward this direction. And after the electron travel for certain time t, you can get the energy acquired from electrical field equals to this equation, this part. So we can derive this term from these three equations, from basic Newton's law. Okay. So if you place a cation, right, in the same electrical field, the cation will also be accelerated by electrical field. And the cation travel along the direction of electrical field. So the cation will travel from left to right. So again, we can calculate the acceleration of the cation equals to the electrical force divided by mass of cation, divided by mass of cation. And if the cation also travel for time period t, the energy acquired by the cation equals to this equation. Okay. And if we compare these two terms, we will find out the energy acquired by electron is much higher than the energy acquired by cation in the same electrical field. In the same electrical field, so the electrons can be accelerated and obtain a large amount of energy. And if the energy of electrons is higher than the ionization energy of atom, once the electron collide with the neutral atom, the neutral atom will be ionized. And this is the most important impact reaction in plasma. And later on we can see this reaction. It is named electron impact ionization. Electron impact ionization. Okay. So this is the way to generate plasma within an electrical field. So you can use the setup of electrical system with the most simple system is the ion system. You can place two electrodes against each other, right? And one electrode is biased negatively, the other one is ground, so that there will be an electrical field between these two electrodes. And the case inside the system between these two electrodes will experience electrical field. And if there are few electrons, few free electrons already exist in your system, these electrons will be accelerated and gain energy. And later on, when you collide with a neutral atom, it will knock out another electron. Another electron, so that the number of electrons will keep increasing. And when it reaches a critical value, the gas will ionize and discharge. Okay. Any questions so far? Okay, so the upper left figure is a quartz tube William Crook used to run the experiment to show that electricity can pass through gas. But when the electricity passes through the gas has already become ionized, and the gas is in a discharge state. So this is the system. So you can use a quartz tube, right? And on the left side of the quartz tube, you can place an electrode. And K here means cathode. So this side is cathode. Cathode is biased negatively from the power supply, from the DC power supply. And the other side is anode. Anode is biased positively. But for the safety, usually the anode is grounded. Right? but there is still a potential drop between cathode and anode, between anode and the cathode. Right. The potential drop divided by the distance between these two electrodes equals to the electrical field. Equals to electric field. So before the gas becomes plasma, the electrical field, right, along this direction at any position, the electrical field is the same. The same. Because there is a uniform potential drop between cathode and anode. Okay. So once you you set up a system like this way, you can control the pressure inside this tube. You can use the pump to evacuate gases so that the pressure becomes smaller than 1 atmospheric pressure. Okay. So when the pressure is adjusted to an optimum condition, and you can apply a voltage between cathode and anode, and then get the gas discharged and form the plasma. Okay. And okay. Okay, so once plasma is generated, and inside the same system, you can see the electrons will travel toward the positive electron. So in this figure, the positive electron is anode, right? And the cation will travel toward the negative electron, toward the cathode. So both electron and the cation carry electricity. Okay, so that electrical current can pass through the gas between these two electrons. Okay, let's take a